Hello everyone, thanks for coming to watch this video. So today we'll be talking about my final year research project on unsupervised machine learning. And the work I've been doing is with the NINIAS European project in order to classify evolved stars. So we will be talking about context, but also kind of keeping it vague so that we can kind of apply it to other contexts as well. So a good place to start here is what actually is machine learning. And I think the best way I describe it in its lowest form is machine learning is simply a tool that can provide data with labels. So for example, let's take a data set full of pictures of dogs and cats, and I've taken the liberty of including a couple cute photos here. And if we were trying to teach a baby the difference between a cat and a dog, well, a good approach that one might take would be to give labels to the two animals, show them many pictures of each one, and, well, theoretically, eventually it would come to a stage where we could show the baby a picture of a cat or a dog, and they'd be able to distinguish it based on the labels we have given them. And this is all well and good if we have labels for the data. So we can say, well, this is clearly a picture of a cat, and this is clearly a picture of a dog. But there are many cases where we do not have labels for the data. And this is where unsupervised machine learning comes in. And the difference here is that machine learning unsupervised does not require labels in order to learn. It basically would sift through the photos and find features on its own. So now we know that unsupervised machine learning is a powerful tool that can be used to help give meaning to large amounts of data. And what kind of data can we apply this to? Well, we know that the universe is a pretty big place, and there's all kinds of new instrumentation constantly coming up, such as the James Webb Telescope, which I'm sure a lot of people know about, that is expected to produce massive amounts of data, and it is quite frankly impossible for human beings, without the help of machine learning, to sift through this data themselves. So, how can we go about using unsupervised machine learning to classify objects in space, in our case specifically stars? And without going too in depth here into astronomy concepts, we will basically be using photometry, which is the light that comes from a star. So what we're hoping for here is that we can take a photometric data set filled with photometric values for lots of different star types, and then apply unsupervised machine learning to it, and hope that it would distinguish features between the different classes of stars, and, well, hopefully have some really cool results. So first things first, we have the photometric dataset, and the data actually does originally have labels in our case, but since we are going in the mindset that we do not have labels, we will not be using them. Although we do have the advantage of being able to measure the accuracy and effectiveness of our clustering and classification algorithms by comparing it to this ground truth. So I suppose if we look at this right plot image here, an ideal scenario for us would be if we can replicate this completely using a machine learning algorithm. So first we tried k-means clustering, which is probably the better known unsupervised clustering algorithm. It's really simple to implement. You just feed it the number of clusters you want. In our case we picked 5 because we knew that there were 5 classes in the original ground truth, and you observe whether the results are successful or not. So in our case we can see that we measured a metric of 65% clustering accuracy, which seems not too bad, but it's not very good. And also we can see quite simply just from the distribution of the clusters that it is nowhere near resembling the ground truth. I mean, originally we had this kind of really nice cluster here, and this large rest cluster here, but it almost seems as if it's just simply been split up into 5 portions quite neatly, which is not what we were going for. So the next things we tried were dbScan and HDBScan, which are slightly more complex algorithms, but they basically work off of density as a metric. So figuring out that the data we were working with was very dense, we experimented with this and actually found some really promising results with HDBScan. So as we can see, we're getting a quite close resemblance to the ground truth here, where like these kleiner clusters that were there originally are being found. The actual clustering metric in terms of accuracy has not increased. And I think this is largely because there are so many outliers, which is something that dbScan and HDBScan accounts for. So all of these blue dots around the green and red cluster are actually classed as noise, and essentially the algorithm has decided that this is not useful data and should not be classed as anything. So essentially what we want to do here is find features in the data and augment or optimize them. And for this we can use feature extraction. So here are some of the things we tried. TSNE, UMAP, and autoencoders. And as you can see, the data has essentially been completely restructured. And the question is, did this actually improve the clustering? And we can happily say, yes, it did. We found with UMAP in particular, we found accuracy was increasing by a large margin. We can see from the image on the right that we now have 86% clustering accuracy. And also the blue dots outliers that we were noticing a lot of before are almost non-existent in the data. So this was a really great result that we were very happy with. Something else that was found was that by combining an autoencoder with UMAP, we found a really, really nice separation of carbon-based and oxygen-based AGB stars, which are these red and purple clusters in the dataset. So this didn't necessarily lead to the highest accuracy results, but was still a very exciting novel finding because we essentially weren't expecting it. These stars really are along the same kind of like age and evolutionary timeline, so they exhibit very similar temperatures and characteristics. So yeah, it was pretty exciting to find this as well. And that's it so far. So thank you very much for your time watching. I will be attending the research conference this year, 2022. So if you're coming along and you're interested, feel free to come by, ask some questions if you want to know anything a bit more in depth, and I'd be absolutely delighted to talk through it with you.